We now turn to a method of heat transfer that you are all familiar with. Anyone who has ever grabbed the handle on an all-metal skittle on the stove knows the handle can get extremely hot. Somehow heat has been transferred directly through the metal skillet and up into the handle. This process of heat transfer is known as conduction. Conduction is the process whereby heat is transferred directly through a material, with any bulk motion of the material playing no role in the transfer. We can consider atoms in a solid, for example, vibrating with kinetic energy. Since heat is a measure of the total internal mechanical energy, atoms in a hotter part of the solid will vibrate with more energy. They collide with adjacent atoms and transfer some of their energy through these collisions. Metals, like copper, are good conductors of heat. They take advantage of electrons that are free to move throughout their volume. These free electrons can transport energy and are responsible for the metal's good thermal conduction. As we will see in Chapter 20, these free electrons are also responsible for a metal's excellent electrical conductivity. Materials that conduct heat well are called thermal conductors, and those that conduct heat poorly are called thermal insulators. As we have mentioned, most metals are excellent thermal conductors, whereas wood, glass, and most plastics are thermal insulators. Thermal insulators have important applications, as there are many instances where heat conduction must be minimized. Virtually all new housing construction incorporates thermal insulation in attics and walls to reduce heating and cooling costs. To illustrate the factors that influence the conduction of heat, consider the figure below, showing heat flowing through a rectangular bar of cross-sectional area A and length L. The ends of the bar are in physical contact with two other bodies, one of which is hot and kept at a constant higher temperature than the other end, which is kept at a constant colder temperature. We will assume the sides of the bar are insulated, so we don't lose any heat to the surroundings. In other words, any transfer of heat from the hotter body will travel along the bar to the colder one. The amount of heat, Q, conducted through the bar depends on several factors. First, Q is proportional to the time during which the conduction of heat takes place. Second, Q is proportional to the temperature difference between the ends of the bar. Thus, a larger temperature difference causes more heat flow. If the bodies in contact with the end of the bar have the same temperature, so that delta T equals 0, then no heat flows down the bar. Third, Q is proportional to the cross-sectional area of the bar. Doubling the cross-sectional area, for example, would allow twice as much heat to flow down the bar. Finally, Q is inversely proportional to the length of the bar. Greater lengths conduct less heat. These proportionalities can be brought together and made an equality using a proportionality constant K, known as the thermal conductivity. The heat Q conducted during a time T through a bar of length L and cross-sectional area A is given by the following, where delta T is the temperature difference between the ends of the bar and K is the thermal conductivity of the material. The SI unit of thermal conductivity is joules per second per meter per Celsius degree. Since the SI unit of power is the joule per second, or watt, the thermal conductivity is also given in units of watts per meter per Celsius degree. Different materials have different thermal conductivities, as the table shows. As we have mentioned previously, metals are really good thermal conductors and have large thermal conductivities. In comparison, liquids and gases generally have small thermal conductivities. In fact, in most fluids, the heat transferred by conduction is small compared to that transferred by convection, when there are strong convection currents. Air, for instance, with its low thermal conductivity, is an excellent thermal insulator when confined to small spaces in which no appreciable convection currents can be established. Goose down, styrofoam, and wool, for example, derive their fine insulating properties in part from the small dead air spaces within them. We take advantage of these dead air spaces too by wearing multiple layers of clothing on cold days. Air becomes trapped between the clothing layers and acts as excellent thermal insulation.